In section 2.7, we're going to investigate inverse functions. The definition of an inverse function is as follows. Suppose we have two functions f and g such that f composed with g of x is equal to x for every x in the domain of g, and also that g composed with f of x is equal to x for every x in the domain of f. If we do the two compositions, f composed with g and g composed with f, if they both produce the output x, then we say that g is the inverse function of f. And then instead of calling it g of x, we would rename it and we would rewrite it as f inverse of x. Rewriting these two conditions using the inverse notation, what it says is that f composed with f inverse of x is equal to x, and that f inverse composed with f of x is equal to x. Intuitively, one of the ways that you want to think about inverse functions is that whatever a function does, its inverse should do the exact opposite. Meaning that if you look at this composition here, if I take x and plug it into the function f is going to be some kind of rule. Again, it could be a chart, a table. Mostly for us, it's some kind of equation where f will assign a value at x. Whatever that assignment or whatever that rule does, if we then take that and apply that to f inverse, if f is the inverse of f, then what it is going to do is going to inverse or reverse whatever we just did, and what we get is the original input x as the output here. Okay. For example, let's show that in example 1, the functions f of x, which is 5 times x, and g of x, which is x divided by 5, are inverses of each other. Whenever this is the particular question, what we need to do is check the two different compositions. Let's first look at f composed with g of x. The inner function is g, the outer function is f. F of x says to take 5 times your input. This time we're using g of x as the input, so I'm going to plug in x divided by 5. The multiplication by 5, the division by 5 cancel, and so that does give us x. We're not quite done yet. We also have to verify it by checking the other composition. Let's look at g composed with f of x. The inner function this time is f. The outermost function is g. G of x as a function says to take the input and divide it by 5. This time our input is f of x, which is 5 times x. And 5x divided by 5 also reduces and gives us x. Thus, by showing that the two compositions produce x, we can say definitively that g is f inverse. So it is true, those two functions are inverses of each other. Let's look at another one. In example 2, we want to show that the functions are inverses of each other. So let's go ahead and do the compositions. F composed with g of x. The inner function is g, the outer function is f. F of x says to take 3 times your input, add 2 to it. What we're plugging in for our input is the function g, which is x minus 2 divided by 3. One of the things that I am kind of a little bit of a stickler on, and it's whenever you're trying to verify this, show obviously the composition written out, but then take your time and go step by step to show exactly how this algebraically simplifies to x. Once we have it plugged in, the first thing to notice is that the multiplication by 3 and the division by 3 cancels. This will leave us with an x minus 2 plus 2. At this point, the subtraction by 2 and addition by 2 cancel, and we do get x. Okay. So far, so good. Let's now check the other composition. G composed with f of x, the function g says to take your input, subtract 2 from it, and then divide it by 3. And what we're plugging in here is going to be f of x, which is 3x plus 2. To simplify this, notice that the plus 2 and the minus 2 cancel. So we get 3x over 3. At this step, the multiplication by 3 and division by 3 cancel, and so once again we do get this equaling out to x. So by showing those two compositions, we have verified that g is indeed the inverse function for f of x. In order to find an inverse of a function, there's a couple steps that we can take to do this. The first step is, given a function f of x, let's revert back to the old school notation, and we're going to call it y equals. So we're going to replace y with f of x. The second step is we are going to interchange the x and the y variable in the expression. What that means is that everywhere you see an x, we're going to put a y, and conversely, everywhere we see a y, we're going to put an x. Once we've done that, we're now going to take the resulting equation and we're going to solve it for the y variable. Once we've solved it for y, the new expression of the form y equals, we're going to revert back to the function notation, except that y equals isn't the same thing as the original function. That actually will be the inverse. Last thing we can do is we can verify that we got the correct answer by showing that the two compositions, f composed with f inverse, as well as f inverse composed with f, give us the original input of x. Let's take a look at example 3. We want to find the inverse of 7x minus 5. So let's do this in steps. Step 1, we're just going to revert back to the y equals notation. So let's call it y equals 7x minus 5. Step 2 is we're going to do the interchange of the variables. Everywhere you see an x, a y, put an x. Everywhere you see an x, put a y, like this. And now for the third step, the next thing that we want to do is we want to go ahead and now solve for y. The first step would be to add 5 to both sides. So we would get x plus 5 equals 7y. The next step would be to divide both sides by 7. So we get x plus 5 divided by 7 equals to y. With the y now by itself, we can say that f inverse of x is equal to x plus 5 divided by 7, and that would be our inverse function. Okay, what's so nice about this is we can actually check this. Let's look at the two compositions. Let's first do f of f inverse of x. F of x is a function that says do 7 times your input and then subtract 5 from it. Here we're using as our input f inverse of x, which we claimed was x plus 5 divided by 7. Notice that the multiplication and division by 7 cancel, so we get x plus 5 minus 5. The addition by 5 and subtraction by 5 cancel, and so that composition gives x. We now need to check f inverse composed with f of x. The outer function is f inverse. F inverse says take your input, add 5 to it, and then divide it by 7, where our input is f of x, which is the expression 7x minus 5. In the numerator, the minus 5 and the plus 5 cancel, so we get 7x over 7. The multiplication and division by 7 cancel, and that leaves us with x. So we found the inverse, we checked it. Our inverse function is x plus 5 divided by 7. Let's take a look at another one. We want to find the inverse of f of x equals the cube root of x minus 1. Again, first step, let's go back to the old notation. Let's call it y equals the cube root of x minus 1. Step 2, we're going to do the interchange. Every y becomes an x. Every x becomes a y. Once we've done that, we now want to take this and solve for y. To get the y by itself, notice that y is under a cube root. To get rid of a cube root, we need to cube both sides. This produces x cubed equals y minus 1. And then the next step would be to add 1 to both sides. We've now successfully gotten the y by itself, and so that is our inverse function. F inverse of x is x cubed plus 1. Again, it's good practice, and you should do this. Let's go ahead and check our work. Let's do f composed with f inverse of x. F of x says to take the cube root of your input minus 1. Here the input is f inverse, which is x cubed plus 1. On the inside, the plus 1 and the minus 1 cancel. Right? Addition by 1, subtraction by 1 are opposite, so they cancel. That now leaves us with the cube root of x cubed, which are inverses. The cube root cancels the cube, and so that does produce the output of x. Let's now look at f inverse of f of x. The outermost function is f inverse. F inverse says take input cubed plus 1. And we're substituting into this the expression for f, which is the cube root of x minus 1. Right off the bat, the cube root and the cube cancel. So we get x minus 1 plus 1. And then the minus 1 and the plus 1 cancel. And so once again, we're left with x. So that verifies and checks that we have the correct inverse. It is x cubed plus 1. One of the things that's very important to consider is not every function will have an inverse. Okay, we've seen earlier in the class that for different types of graphs, a graph will define a function of x if it passes the what we call the vertical line test. So recall that the vertical line test can be used to determine whether or not a graph defines a function. So not all graphs give functions. Similarly, not all functions will have inverses. Okay, to have an inverse is a very special property of a function, and it's those functions that are one-to-one that are the ones that have inverses. We say that a function is one-to-one, also written 1, 1, if each value in the domain corresponds to a unique value in the range. Okay? So remember, to be a function, each value in the domain had to correspond to exactly one value in the range. To be one-to-one, you still have to have that property because it still needs to be a function. But what this is kind of saying is that each value in the domain produces a unique value in the range. Okay, so unique inputs would produce unique outputs. A very nice function, one we're very comfortable with, f of x equals to x squared, although it's a function, if we look at its graph, right, it's a parabola like this, it passes the vertical line test, so f of x equals x squared is a function, but it's not a one-to-one function. And to see why it's not a one-to-one function, let's consider substituting in and evaluating the function at -2 and 2. If we plug -2 in, we get -2 squared, which is 4. And if we plug +2 in, we get the same output of 4. So what that means is that we have two values of x that produce the same output. And because of that, that means that f is not one-to-one. Okay? Visually, it would fail what we call the horizontal line test. The horizontal line test can be used to determine whether or not a graph of a function is one-to-one. If each horizontal line intersects the graph in at most one point, then the function would be one-to-one. So for example, this kind of graph here, which looks something like a little bit like x cubed, no matter how many horizontal lines I draw, each horizontal line intersects the graph in at most one point, and that means that this graph would be that of a one-to-one function. However, the function we just saw, x squared, there is at least one horizontal line that intersects the graph in more than one point, and because of that, this graph is not one-to-one, because it would fail the horizontal line test. The reason why we care so much about one-to-one functions is that it's one-to-one functions that have inverses. Okay, if a function is one-to-one, then it will have an inverse. So according to the horizontal line test, this function, the one that's graphed in green, it is one-to-one, and because of that, it will have an inverse. Whereas the graph over here, the graph of x squared, it fails the horizontal line test. It is not one-to-one, and therefore does not have an inverse. If we take a look at example 5, we are given two different graphs, and we want to determine, first of all, whether the functions are one-to-one, and in addition to that, state whether they would have an inverse or not. If we look at example 5, we see that no matter what horizontal line we draw, we're going to get at most one point of intersection. That means that this graph is one-to-one. And because it's one-to-one, that means that it will have an inverse. However, if we look at the graph over here, there are many horizontal lines, but in particular, you can find at least one horizontal line that intersects the graph in more than one place. So because of that, this graph is not one-to-one. And that means that it does not have an inverse. So this one does not have an inverse. The next thing we're going to come to is the relationship between a graph of f and f inverse. If you kind of think about the process, so one of the things that we were doing whenever we were graphing, or whenever we were finding f inverse, is we had this step where we interchanged the x and the y variable. Graphically, the implication of that is going to be the following. Let's suppose we have a point, and let's call the point x comma y, which is on the graph of f. Whenever we interchange the point x and y, if everywhere you see an x you put a y, and everywhere you see a y you put an x, that means that the corresponding point y comma x will be on the graph of f inverse. For instance, if 2 comma 4 is on the graph of f, then the point 4 comma 2, which is simply found by reversing the x and the y coordinates, will be on the graph of f inverse. Okay. And graphically, this is also going to create a symmetry with respect to the line y equals to x. The reason why y equals to x is a symmetry for the function and its inverse is for the following reason. Let's suppose you have an ordered pair x comma y. The points on the curve y equals to x have both the same x and the y coordinate. For example, if I pick on, let's say, 3 comma 3, 3 comma 3 is on the line y equals to x because it satisfies that equation, right? You plug in 3 for x, you plug in 3 for y, and you get the same numbers that are equal. Well, if you take those x and y values and you interchange them, you still end up with the same point. And in math, there's a term for that. It's called an invariant. So that doesn't change under this transformation, and that's why it actually ends up being our line of symmetry here. So if we look at, for example, let's suppose we have the graph of the function in blue. Suppose this is the graph of your function f of x. If you simply take that function and reflect it across the line y equals to x, remember, every point of the form a comma b will produce the point b comma a on the graph of f inverse. As a line reflection, what this means is pick any point on the curve of f connect it perpendicularly to the straight line, whatever that distance is. If you continue that line on the other side of that line of symmetry, the same distance, you will come up with yet another point that will be on the graph of the inverse function. As an example, let's suppose they give us the graph of f of x below, and we want to find the graph of f inverse. In order to help us, let's kind of create a table here for f inverse of x. Notice that we have these ordered pairs that are on the graph of f. We have -3, -2, -1, 0, and also 4, 2. If we invert those pairs, if we flip-flop the x and the y coordinates, then that means that the ordered pair -2, -3, 0, -1, as well as the points 2, 4, will lie on the graph of f inverse. So let's go ahead and plot those. -2, -3 would be here. 0, -1 would be here. And then 2, 4 would be right here. The graph of f was kind of piecewise linear. So if we just kind of connect these via straight lines, that would give us the graph in orange, which would be the graph of f inverse of x. And I'll also go ahead, let me draw the line of symmetry here. Again, the line of symmetry is a line y equals to x. If you were to take these two graphs, imagine if the plane was like a piece of paper. And if you could fold this paper along that crease, that line of symmetry, the two graphs would perfectly match up with each other. Let's take a look at example 7. They ask us to find the inverse of f of x equals x squared minus 1 if x is greater than or equal to 0. Okay. So first of all, some of you might look at this. We know how to graph this function, by the way, from our transformation section. This would be the graph of x squared with a vertical shift down by 1 unit. So this graph kind of looks like this. And if we go back a couple minutes ago, we'd say, well, wait a minute. This function does not satisfy the horizontal line test. It's not one-to-one, and therefore this graph should not have an inverse, which is true of the graph x squared minus 1. But if we also add in the restriction that x has to be greater than or equal to 0, then essentially what's happening is we only end up with this portion of the graph. Here's -1. And we have just kind of like the right half of the curve. This little piece would pass the horizontal line test, which means that this part should have an inverse. Let's go ahead and find the inverse. To do so, remember step 1, replace f of x with y. Step 2, we're going to interchange the x and the y. And now step 3, we need to solve this for y. The first step would be to add 1 to both sides. We get x plus 1 equals to y squared. To get the y by itself, the next step would be to take the square root of both sides. Now, normally speaking, we would have a positive and a negative root. But because of this restriction, because we're requiring x to be greater than or equal to 0, that gives us just the positive root. Okay? So we don't have two pieces here. We do just have one piece for our inverse. The square root and the square cancel. So we get the square root of x plus 1 is equal to y. That y is now our inverse function. So we get f inverse of x is equal to the square root of x plus 1. They now want us to kind of go ahead and graph these two functions on the same set of axes. So let's go ahead and do that. Remember, f of x was x squared minus 1 with a restricted domain of x greater than or equal to 0, that's going to look like this. Our inverse function, we just solved for it, is the square root of x plus 1. And let me do that in a slightly different color so it stands out. So f inverse of x is the square root of x plus 1. That's going to be a horizontal shift 1 unit to the left of the square root function. And it's going to look like that. So this is the graph of f inverse. This is the graph of f. And I can also impose the line of symmetry in there, which would look like this. So once again, we see the two functions, and they're symmetric with respect to the line y equals to x. There's one more part to this, and this is a very important concept, something you absolutely should know, is we're asked to compare the domain and the range for f and for f inverse and see how they compare to each other. So let's start. We have f of x. We have f inverse of x. Let's find the domain of f, the range of f. We're also going to find the domain of f inverse and the range of f inverse. Luckily, because we've already graphed this, we can do this directly off of the graph. If we look at the function f of x, the domain, remember, domain, that's when you're talking about the set of x values. The curve in blue goes as far to the left as 0, and then it goes all the way to the right towards infinity. So the domain of this is going to be from 0 to infinity. If we look at the range of the function in blue, now we're looking on the y-axis. How low to how high does the graph go? It goes as low as the y value -1, and it shoots all the way up towards positive infinity. So the range of f is from -1 to infinity. Let's now do the same thing. Let's take a look at the graph of f inverse. For f inverse, its domain would again be how far left to how far right. F inverse goes as far to the left as -1, and it goes all the way to the right. So that goes from -1 to infinity. And then for the range of f inverse, we need to ask the question, well, how low to how high does it go? The lowest point on the graph of f inverse is this one here, which is at 0, and it does go all the way up towards positive infinity. So the range for f inverse is from 0 to infinity. If we compare these two, look at what's happening here. The domain of f as a set is actually equal to the range of f inverse. And the range of f is equal to the domain of the inverse function. That's not a coincidence. That always happens. That's a relationship that definitely holds. And again, that's a consequence of that step 2 when we find inverses. Remember, typically we think of domains as being x values and range as being the y values. Well, in step 2 of finding the inverse, what we're doing is we're interchanging the x and the y variables. And in essence, what that does is that interchanges the domains and the ranges of the two. So the domain of a function is equal to the range of its inverse, and the range of the function is the domain of its inverse. So that's a very important relationship. Please make sure you know that key fact. So domain of f is equal to the range of its inverse function, and the range of f is equal to the domain of the inverse. And that's the relationship between the two.